Thank you very much. My name is Adrian van Kan, and I have the distinct pleasure to tell you today about work that I've done on simulating rotating convection at very small but finite Ekman numbers. As part of this work, I had the privilege and honor to work with Keith Julien as part of a joint NSF project between CU Boulder and UC Berkeley. And really, many of the ideas that I'll be describing throughout the talk have been developed by Keith Julien and Egger Knobloch, as well as collaborators over the last years and really decades. So I consider myself very fortunate to have been in the right place at the right time, to really have had the chance to bring to fruition some of the very insightful ideas that Keith had developed. This work is also done in collaboration with Benjamin Miquel in Lyon and Jeff Vessel in Edinburgh, and I acknowledge funding from the National Science Foundation and the German Research Foundation. So without further ado, I'll begin by saying that this talk has 5 parts. I'll very briefly go through an introduction. Some of it, much of it will be repetitive, but please bear with me, to set up a discussion of the reduced non-hydrostatic quasi-geostrophic equations, which will, as I will explain, inform an improved numerical formulation of the Navier-Stokes equations to perform efficient simulations at very low but finite Ekman numbers. I'll present various numerical results obtained using this, what we call the rescaled incompressible Navier-Stokes equations. And finally, I'll give some conclusions and an outlook on next steps. So I don't think I need to spend a lot of time convincing you that rotating convection is important and a key driving mechanism in planetary interiors, stellar interiors, oceans, and atmospheres. In addition to being in an extreme parameter regime, these systems are also complicated due to spherical geometry, compressibility, and other effects, which I will not consider here. And instead, I will focus, as has been the case in many talks, on an idealized setup, namely a Cartesian fluid layer with a rotation axis anti-parallel to gravity. So I'll call this the polar setup. And this system, heated from below, cooled from above, is described by 3 non-dimensional parameters that we've seen sort of enough at this point. I'll still go through them quickly. So the Ekman number controls the strength of rotation, with small Ekman numbers indicating rapid rotation, the Rayleigh number quantifying the thermal forcing strength, large Rayleigh numbers indicating strong thermal forcing, and the Prandtl number characterizing the fluid in question. The governing equations for the fluid in between these 2 boundaries I will consider as a Boussinesq fluid, and these are the non-dimensional equations. I stress that these have been non-dimensionalized with height of the layer as the unit for length, a viscous diffusion time scale based on that length scale to non-dimensionalized time, and temperature being non-dimensionalized by the temperature drop across the layer. This theta here is the deviation from a conductive background state. At the risk of being extremely explicit here, I'll just specify that I care about constant temperature boundary conditions at the top and bottom, and the velocity, whose components I will denote by u, v, and w, is assumed to be stress-free at the top. Impenetrable boundaries are imposed at the top and bottom, and I have periodic boundaries in the horizontal, so I don't need to worry about wall modes, although we've learned a lot of interesting things about them. They won't appear here. So now that we've specified some input parameters and we solve our system, we need to specify what do we actually want to get out of the system. And so we need to specify output parameters, such as the Nusselt number that's been mentioned many times, or the RMS velocity, based on which we can define Reynolds number, say, in terms of the height of the fluid layer. Now, this is, of course, a classical system that we all know and love. And the challenge in this system is that the interesting parameter regime is very extreme. So this doubly logarithmic parameter space illustrates that. On the x-axis is the Ekman number. Small Ekman numbers is fast rotation. High Reynolds numbers on the y-axis indicate strong turbulence. And these symbols here indicate estimates of geo and astrophysical systems that are the desirable parameter values. On the other hand, these shaded regions indicate lab experiments and numerical simulations at the state of the art. And clearly, there is an order of magnitude gap in both of these parameters between what we can do and what we want to do. Now, to be a little more explicit here, the lowest Ekman numbers achieved in direct numerical simulations of plane layer Rayleigh-Bénard convection, to my knowledge, is this paper or 2 papers by Song, Shishkina, and Zhu, where in JFM last year, they investigated Ekman number of 5 times 10 to the minus 9 with no slip boundary conditions. This is really an impressive feat and required an immense computational effort. And in the spherical domain, things are even more tricky, and I believe the lowest Ekman numbers obtained to date is 10 to the minus 7 in this case, which is quite a bit higher. In laboratory experiments, the state-of-the-art is, I believe, currently the Eindhoven experiment with 5 times 10 to the minus 9 as the tallest experiment. And these, I should stress, are all Herculean efforts to really push the boundaries to the lowest Ekman numbers we can obtain using these methods. However, even the state-of-the-art is really very far from what we want to do in these applications. And so in this talk, I'll try to present one way that we've devised to enter a regime at much lower Ekman numbers. Okay, key challenges that one has to face when simulating rapidly rotating flows are dealing with fast inertial waves, which are waves whose restoring force is the Coriolis force, and which are much faster than, say, the slowly evolving turbulence. And this can lead to prohibitive time-stepping requirements. But at the spatial level, there are also highly anisotropic structures, namely columnar structures, with aspect ratio that increases as the Ekman number decreases, with Ekman to the power 1/3. And we've heard of the Taylor-Proudman constraint many times. This is the incarnation of that. Another level at which these flows are difficult is if no slip boundaries are present, then Ekman layers form. And these features require careful choice of resolution to accurately resolve things. Oops, that's so wrong. Okay. And these very disparate time and space scales really present a challenge to numerical approaches. When we discretize these problems, we can generate numerical arrows. And so the question is, how can we tackle simulations at very low Ekman numbers? And I'll describe, first of all, the approach of asymptotics, which informs, as I will describe later, adequate numerical approaches in this regime. Before I do that, though, and I'm aware that a lot of this is repetitive, I'll just reiterate what we've heard several times on linear stability of rapidly rotating convection. We can linearize about the conduction state and find a normal mode solution with a growth rate sigma, and its real part passes through 0 at a critical Rayleigh number, and I'll be interested in Prandtl number equals 1 for all of my simulations. So I'm in the non-oscillatory regime, and the interesting thing is that the critical Rayleigh number increases like the Ekman number to the power minus 4/3. And this indicates, as I'm sure most of you are aware, that rotation suppresses convection, because we need to crank up the thermal forcing when the Ekman number goes down. On the other hand, the most unstable mode that emerges as part of this instability has a horizontal wave number that is very large. So it is a large number. Ekman going to 0 indicates the critical wave number becomes large. In other words, these are thin columnar structures. Horizontal wavelength is large, horizontal length scale is small. Okay, so these are just some key features to keep in mind from linear stability theory. But linear stability theory is not all we want. We want nonlinear. And to do that, we can resort to asymptotics. And this is the theory of non-hydrostatic quasi-geostrophy. And I'll encourage you to look at this paper, which has a lot of details on this. We'll begin by making a change of units informed by this linear stability analysis. So we define a parameter epsilon, which is Ekman to the power 1/3. It doesn't have to be small at this stage. It's just a naming. So we're just naming epsilon. And we define this Rayleigh tilde as epsilon to the power 4 times Rayleigh. I'm aware this is slightly different from what other talks have used. It's not Rayleigh divided by the critical value of the Rayleigh number. There's a constant factor to convert between these two conventions. And these things are clearly motivated by the appearance of this 1/3 power, the Ekman number, in linear stability theory.
Can I just ask?
Yeah.
To me, it's operationally the same thing. Philosophically, where's the difference you're pointing out? In other words, Ekman to the 4th power.
No, this is cosmetic, if you will. Yeah. I'm just simplifying things for us. Yeah, thanks. What is slightly more physical is that from linear stability theory, one insight that we gained is that a crucial length scale in this problem is epsilon times the height of the layer, rather than the layer height itself, in terms of the horizontal scale of these structures. And so it makes sense to measure length in terms of those units. Again, this is an equivalent reformulation of the problem. It doesn't add any information, but it turns out to be convenient. So we can measure length in units of epsilon times the layer height and time in units of the viscous diffusion time based on that length scale. And then we construct a velocity scale based on that. And this leads to just some transformations in the equation. So I started with this non-dimensional equation at the beginning, which was non-dimensionalized with some choice of scales. Here I used a slightly different unit. So by this transformation, I convert to this set of units. And it turns out the pressure, also, if one transforms the pressure this way, it turns out to be convenient because it leads to this set of equations. Here, the powers of the Ekman number are slightly reshuffled compared to the original system. But one can already see here that there's a 1 over epsilon in front of the Coriolis force and a 1 over epsilon in front of the pressure gradient. And if we anticipate the kind of balances that we might see in the limit of small epsilon, this is a nice place to start. But so far, I haven't done anything. I've just measured things in different units. Now, this is where kind of the fun starts. We can consider the limit of epsilon going to 0. And it's a distinguished limit where the Rayleigh number becomes large and the Ekman number becomes small, so that the product of Rayleigh times Ekman to the 4/3 is a constant. We can introduce then slow variables, capital Z and capital T, that incorporate these powers of the small parameter epsilon, in addition to the fast variables, X, Y, Z, and T. And the interest of doing this is that we want to study the slow, large-scale dynamics of the system. And the key step is that when epsilon is very small, we can treat these as independent variables. The large and slow scales are independent from the fast scales. And this leads just to a transformation or substitution of these derivative operators. And since we're interested in the long time and sort of slow and large-scale dynamics, it's natural to decompose all fields, including velocity, pressure, and temperature, into an average, a mean component that just depends on these slow variables and the fast variables. And so this overline notation is just the average over the fast variables. Then we really start doing the asymptotic expansion part of this endeavor. So we take all our fields, including mean and fluctuation, and we expand them in the small parameter epsilon. And then the idea is to solve order by order in this small parameter epsilon. And I won't bore you with the details here, but I just want to sort of give the key highlights, which is that in the horizontal momentum equation, the balance that pops out is the geostrophic balance between the Coriolis force and the pressure gradient that we've already heard about many times. And it's a key balance. It governs the large scales of the atmosphere in particular, which is why low pressure areas in the northern hemisphere turn counterclockwise. But it's not all. We also learned something else, namely that the leading order fluctuation fields actually are independent of the fast variable z. And that is very convenient because we're interested in making things, we're interested in how things depend on the slow and slow space and time variables. Okay. Now it's not quite as easy when one goes to the following order in the small parameter epsilon. And again, I won't bore you with the details, but the key step is that one recognizes that this second order term W2 can grow with the fast scale Z. And that's called secular growth. And it's dangerous in asymptotics because if this W2 becomes of order 1 over epsilon, then epsilon squared times W2 becomes comparable with the previous term. And that breaks the asymptotic structure of our expansion. And so everything breaks down. To avoid that, one can impose a solvability condition. And this is what leads to a closed set of equations, the so-called non-hydrostatic quasi-geostrophic equations. Here I've dropped the indices for simplicity. And this is one way to write the equations. They involve the vertical velocity, the vertical vorticity, the temperature fluctuation, and the mean temperature. And they are reduced equations in the following sense. First of all, they only involve z through the slow vertical coordinate. So there's no more little z in this equation. And that's very good because we're interested in how things depend on the slow variables. In addition, advection is only through the horizontal velocity. And diffusion operators only have horizontal contributions. And these key features, in addition to the fact that epsilon appears nowhere explicitly in these equations, have the effect of filtering fast waves, first of all, in this equation. And that's key because it simplifies actually integrating these equations enormously. And also, it removes Ekman layers because of the structure of the diffusion terms. So these equations have been integrated and shown to contain geostrophic turbulence, a plume regime, and many interesting dynamical phenomena, which will not be the focus here. I guess, so as an aside, since we're in the Institute of Pure and Applied Mathematics, these equations have also been of interest in pure mathematics. And there have been some attempts to prove global existence and uniqueness of solutions to equations that are similar to these equations, the 3D Hasegawa-Mima equations. And this could be done when there's a little added diffusion, a little added dissipation in the vorticity equation. But that's really just an aside. The more important point about these equations is that they have a symmetry, several symmetries, really. So first of all, they are translation invariant. That's not very surprising, but they also have an equivariance under reflection. So if I change the sign of x, and I accordingly change the sign of the fields, as shown here, then actually the equations don't change. And there's a similar symmetry when I change the sign of y and accordingly change the sign of the fields. And what this means is that there's an absence of handedness in the system because I've actually changed the sign of vorticity and the equations remain unchanged. So these are some key properties of these equations. But while they've been very successful, they also have a drawback. That is, they were derived assuming an asymptotically small Ekman number. In reality, the Ekman number is never asymptotically small. It is at most small but finite. So we have to ask, at which point do these equations begin to hold? And can we study the sort of the convergence towards these equations? Okay. And to answer questions of this type, I started to work on the rescaled incompressible Navier-Stokes equation. That's what I will describe now. So we start with the same set of equations that went into the machinery of asymptotics. So before we did asymptotics, we had this set of equations where we measured length in horizontal scales and had transformed accordingly. The idea is now not to do asymptotics, but to use the scalings, the leading order scaling relations that we found in the asymptotics, and dial them into these equations, but without throwing away any terms. So it does sound a little bit too simple. It's really just two steps in addition to this equation. So the first thing is that we adopt anisotropic length scales, such that derivative operators, such as the Laplacian here, become horizontally dominated. So the power of epsilon, Ekman to the power 1/3, appears in front of the vertical derivatives. And here I will just denote z, the vertical coordinate, since I'm not doing asymptotics. And the material derivative similarly becomes horizontally dominated. So all I've done here is really just take into account the very slender geometry of these structures that I've mentioned before. The horizontal scale is epsilon times the height of the layer, but leads to very large aspect ratio structures. And the second step, which I didn't emphasize in the asymptotics, but one finds that the temperature fluctuations, which are fluctuations away from a horizontal average, are actually an order of epsilon smaller in the asymptotics. And just by taking that into account, we can take into account explicitly this power of epsilon that we found in the asymptotics to remove the smallness of this temperature fluctuation field. Now, I don't want to show you necessarily go through all the details of these equations, but I'll show just the horizontal fluctuation component of these equations. This is the momentum equation, and we see that this rescaling, what has it done? Well, we still have an epsilon to the power -1 in front of the Coriolis force, an epsilon to the power minus 1 in front of the pressure gradient. But interestingly, the buoyancy force just involves this order 1 coefficient, which is the reduced Rayleigh number. And that's very good for numerics. We've gone from the Rayleigh number, which is a very large number, and the Ekman number, which is a very small number, to this combination of the reduced Rayleigh number, which naturally appears in the full equation now, just by rescaling. And so we have this order 1 coefficient, which is numerically very convenient. The temperature fluctuation is coupled to velocity and the horizontally average temperature. And the horizontally average temperature itself obeys this equation with an advective term and a diffusive term. And then there's a time derivative term, which at first seems kind of scary because there is an epsilon to the minus 2 prefactor here. So things might really be quite tricky. It turns out, however, that the horizontally average temperature, when the horizontal domain size is sufficiently large, does not vary much. And so this d by dt of the mean horizontal temperature is small, even when multiplied by epsilon to the power minus 2. And that's an empirical finding. That's not something that comes out of the theory. But that means we can neglect this term provided sufficiently large domains. And that's something that was already discovered in the context of the reduced equations. So I've gone through a lot of an ordeal here, really just rescaling my equations. I haven't added or yeah.
Why do you keep the 1 over epsilon in terms of the pressure?
Well, it's just a convenient choice because I know that I'll have leading order geostrophic balance. I can, of course, rescale pressure and absorb the epsilon.
But numerically, it would be more convenient to keep it like that?
I think it might not make such a big difference numerically, but I think, formally speaking, I mean, I'm not sure it will make a big difference. We have a choice because pressure being the Lagrange multiplier, just enforcing incompressibility, I don't think it might make such a big difference. But here, visually, we can already anticipate the right leading order balances in the equation.
Adrian, I missed it. What was the dt with epsilon? What did it mean?
Oh, this is the slow time derivative that we found in the asymptotic equation. So if we went back to the asymptotics, you see the mean temperature equation here also contains a del by del capital T. Yeah. This is the derivative with respect to the slow time variable, and that just pops out also when you just do the rescaling.
Okay. So the dt epsilon includes the slow variables. So Rens also includes the capital Z and capital T of the asymptotic.
Well, I mean, it only includes, in a sense, if you look at the, if you look at this, I mean, I really only have the slow scale, in a sense, yeah. And that it's not, the reason why this works is that in the reduced equations, you just end up having the slow scale. So we kind of anticipate this. Yeah.
In the dominant geostrophic balance, you have two boundary conditions. You have two boundary conditions on the velocity, but you only have the derivative is only first order in pressure gradient. So how do you solve this equation?
So are you talking about the reduced equations? Or?
Yeah. For the geostrophic balance, you need to have the cross balanced by the pressure gradient.
Yes, yeah.
You have one bottom boundary condition and the top boundary condition on the velocity. But you only have the one derivative on the pressure. So actually, you have two boundary conditions, but your PDE is first order. So how do you solve this equation?
It's second order. There's two z derivatives in equation 1 and 2.
I mean, if you look at the combination of this equation and this equation, it appears in both of these. So maybe that's answering the question.
No, I mean the first order, the epsilon to power of minus 1.
There is no problem, so you have no variation.
Oh, no z variation. Yeah.
For the boundary condition also.
Yeah.
So it's the same.
Yeah.
But if we have a constant velocity, suppose we have a velocity w is equal to 0, so your pressure will be always constant, the color? Or?
Yeah, I mean, maybe we can discuss this afterwards. Is that okay? Because, but yeah, I mean, I think I kind of see what the question is, but maybe in the interest of time, I think I'll move on if that's okay. So let's see. So we have rescaled our equations without throwing away any terms, but based on the scaling laws, the leading order scaling laws in the asymptotics. So was this any good? Okay, so the only way to find out is try to solve it. And there are details in these two preprints. Just for specificity, we use a spectral PD solver called Coral, developed by Ben Mikkel, which uses a Fourier basis in the horizontal, since we have periodic boundary conditions, and a Chebyshev basis in the vertical. And kind of schematically, our problem can be written in this form, where V is a state vector, it's not velocity. V is kind of the vector that contains all our fields, and there's this linear operator Li that contains the information about the Ekman number. And that's really where a lot of the trouble comes from. And then we have a nonlinear term due to advection on the right-hand side. When we discretize this, these operators become matrices, and then if we want to assess the numerical accuracy of our scheme at low Ekman numbers, we can do this in two ways. We could either compute what's called the condition number of the matrices on the right-hand side to quantify the kind of sensitivity of the solution to errors in this nonlinear right-hand side. What I'll do instead, for reasons just of time, is to discuss the generalized eigenvalue problem of this operator of this combination of matrices on the right-hand side. So if I substitute, if I look for sort of an eigenvalue to this left-hand side, and the eigenvalue being S, it's a complex eigenvalue in general, then I can plot that eigenvalue in the complex plane. There will be many such eigenvalues because I've discretized and have a high-dimensional problem. This is various different panels showing different Ekman numbers. On the y-axis is the imaginary part of the growth rate. On the x-axis is the real part. Black lines indicate the exact spectrum, which one can compute analytically. The colored symbols indicate numerically computed eigenvalues. And when the Ekman number here is 10 to the minus 7, and then it's 10 to the minus 9, 10 to the minus 10, 10 to the minus 11, I'm showing these numerically computed eigenvalues for the unrescaled Boussinesq Navier-Stokes system, the very first non-dimensional equation I showed in this talk, for different numbers of modes in the vertical direction. And here the horizontal wave number is fixed, and I fix some parameters. Crucially, I'm under the threshold for convection. So I don't expect any exponential growth in this case. When I look on the left, the colored symbols agree very well with the black line, which indicates that the numerical scheme is accurate at Ekman number 10 to the minus 7. As I decrease the Ekman number, however, there's a worse agreement between these two. And in particular, there are modes here, these green dots, and this becomes worse at lower Ekman numbers. These modes, they have positive real part, which means they're growing modes. They're spurious growing modes, because we don't expect any growing modes at this set of parameters. We can repeat the same game in the rescaled equation. So at the bottom, I'm showing, once again, the eigenvalues in the complex plane for 4 different Ekman numbers. They're not the same Ekman numbers. I'm starting here at 10 to the minus 6, and then 10 to the minus 9, 12, and 15. And as before, at moderate Ekman numbers, I agree very well. But then as I reduce the Ekman number, the agreement between the numerical eigenvalues and the exact spectrum remains satisfactory, even at very small Ekman numbers, down to Ekman number 10 to the minus 15. And so we've eliminated the spurious instability by effectively accurately preconditioning our matrices. What we have done is we have eliminated all the large prefactors and the small prefactors in the equations just by anticipating how things will scale with my small parameter. And this has led to much more efficient numerics. Okay, so...
Sorry, Adrian?
Yeah.
What are the blue points?
Oh, the blue points is another formulation of the equation based on vorticity and velocity. And so they do even better than the primitive variable formulation. That's a great point. I didn't necessarily want to get into this. But there are different ways we can rewrite the equations, and we end up with slightly different accuracy. Okay, this was linear though, and I emphasized before we care about turbulent nonlinear dynamics. So let's see what we can do. We solve the rescaled equations now again with stress-free boundaries. I will not go anywhere else in this talk, only stress-free boundaries. We integrate from rest essentially with small-scale noise, and we're able to do this over a wide range of Ekman numbers. This is really the key, from order 1 or sort of not very small Ekman numbers to rather small Ekman numbers, down to 10 to the minus 15. And this is 6 orders of magnitude beyond what had previously been done. I'll fix the Prandtl number at unity. I agree with what we heard in yesterday's talk that Prandtl number equals 1 is sort of maybe a starting point, but we really need to go beyond that. I won't do that in this talk. Because of my rescaling, I naturally end up with a very slender domain that's of horizontal extent proportional to the Ekman number to the power 1/3, but of order h in the vertical. And specifically, I'll pick 10 times the critical wavelength as my horizontal domain size in both directions. And this has been shown to be sufficiently large in the context of the reduced equations. Resolution requirements include resolving the thermal boundary layers at the top and bottom, and also resolving the energy dissipation scale in the horizontal. And I'll give a small spoiler before I go into the details. We'll see that the full equations seem to converge to the non-hydrostatic QG equations at sufficiently small Ekman. But what's sufficiently small? Okay. First of all, do we really believe this? I showed the linear spectra, but maybe we want to have more of a validation. For that, we integrated the nonlinear equations at different Ekman numbers and different Rayleigh numbers, reproducing data from this paper by Kühnen and collaborators published in JFM in 2016, where they reported explicitly the Nusselt number. That's really one of the reasons why we chose this work to reproduce. And that's represented by the diamonds in blue and green. And in yellow, I'm showing the results obtained with these rescaled equations, where the circle indicates the mean, and then there's a standard deviation. That's the arrow bar. So there's quite good agreement between these two different studies. And I should emphasize, this is a completely different code with finite difference schemes. And so there's really quite a lot of difference between these two codes, and yet they agree rather well here. Okay, so we can reproduce Nusselt numbers from the literature, but we really want to look at what the solutions look like. So this is the vertically averaged vertical vorticity at different Ekman numbers. On the right is Ekman number 10 to the minus 6, and it's reducing to the left, so it's rotating faster on the left. This is really a measure of the bulk flow, because I've averaged over the volume. Boundary layers are pretty thin. So what this tells me is something about the bulk flow. And on the very right here, I should say this is for Rayleigh tilde equals 120, which is more than 10 times supercritical. And on the very right, we see that the cyclone is dominant compared to the anticyclonic vorticity. Anticyclonic vorticity is weak and diffuse. The cyclone is strong and localized. As I reduce the Ekman number, this asymmetry reduces, and I find at Ekman number of 10 to the minus 15 that, at least by eye in this snapshot, this is a turbulent flow that fluctuates, but in this snapshot, it looks like the asymmetry has been reduced significantly. Well, we can get better than that. We can do statistics, and we can measure the skewness of this vorticity field averaged over time, because once again, this is a fluctuating field. And this is the Ekman number on the x-axis, the time average skewness of this vorticity field on the y-axis. And at very low Ekman numbers, 10 to the minus 15, this is close to 0, which agrees with what we expect from the non-hydrostatic QG equations, because it has this symmetry that we can reverse the sign of vorticity, and there should be no difference between cyclones and anticyclones, statistically. And that's borne out at low Ekman numbers. However, as we cross Ekman number around 10 to the minus 9, we see that there's a departure from this, and that's where the cyclonic dominance sets in. Okay, yes. So the symmetries of the non-hydrostatic QG equations are in fact respected at sufficiently low Ekman numbers here, smaller than 10 to the minus 9. This was the bulk flow, but we can also look at the boundary layers. What I'm showing here is a snapshot of different fields, the vertical vorticity, the temperature fluctuation, and the vertical velocity at different Ekman numbers inside the bottom thermal boundary layer. So I'm close to the bottom plate. And it's a lot of information. I won't go through everything, but we can start on the right again. And we see that also in the boundary layer, the cyclonic structure is dominant when the Ekman number is sufficiently large. But as I reduce the Ekman number, this asymmetry is reduced. And in addition, when I'm at intermediate Ekman numbers, here 10 to the minus 8, we see that there are these shielded vortices of some sort, which have a signature also in the temperature fluctuation and in the vertical velocity field. And now this is just a snapshot. I hope those movies work. Yeah. So it turns out that these are actually quite transient. So they pop in and out of existence. But especially in the temperature field, we can see that they're quite strong and localized structures. Okay. So the takeaway here is that there is qualitatively distinct boundary layer dynamics at Ekman number 10 to the minus 15 and 10 to the minus 8. And what I will argue is that this is related to the loss of geostrophic balance in the boundary layer. Okay. This was visual, and let's get quantitative once again. So we can measure the Nusselt number. I showed some Nusselt numbers before, but how do we measure them? Well, we take time series at different, say here, fixed reduced Rayleigh number and Ekman number, and then we can time average over this turbulent time series, fluctuating time series. And we rescale by the diffusivity-free scaling law that we might anticipate. So this is a kind of rescaled Nusselt number based on that scaling law, plotted as a function of the Taylor number here. So rotation is fast on the right and it's slow on the left. So as I pick up at a fixed reduced Rayleigh number, as I pick up the Taylor number, initially the heat transport increases and then it overshoots, at least in this rescaled way of plotting it. We see that it overshoots and then it, sorry, I take that back. The Nusselt number overshoots, and this is not due to the rescaling. And it plummets back down to a constant value. The constant value agrees with a dashed line. What is the dashed line? The dashed line is the prediction of this reduced non-hydrostatic QG model. And that is another indicator that, in fact, we have the global statistics in agreement between the full equations and the reduced equations provided sufficiently low Ekman numbers. But there's more information here. We can also look at how and when do we depart from this, say, reduced branch of this dynamics. And that is indicated by these dashed lines, or rather dashed dotted lines, sorry. So the point where the Nusselt number departs from this constant value is at least compatible with these dashed lines. And these dashed lines represent a theoretical prediction based on boundary layer theory from this 2012 paper by Julien and coworkers, where they computed the expected Ekman number to, say here, Rayleigh number relation when the local convective Rossby number in the boundary layer is equal to 1. So this is where you expect the boundary layer to go from geostrophic dynamics to ageostrophic dynamics. And it seems to line up with where these curves depart from the constant. So that's number one. But why do they depart to the top? Well, our understanding of this is that as the boundary layer loses geostrophic constraint, you start having these additional flow structures that I showed here, for instance, these shielded vortices, which are transient, but in a time average sense, they contribute they make up a significant contribution to the flow, and they are very confined in the boundary layer. What does that mean? Well, they're high amplitude and they're confined, so they have strong vertical gradients. These gradients lead to dissipation, and dissipation by the power integral relations is directly tied to the heat transport, the Nusselt number. And I won't go into the details, but that is the theory that we have for why these Nusselt numbers depart to the top. And then eventually, as we reduce the Ekman number at fixed reduced Rayleigh number, we are reducing supercriticality, and the convection has to stop at some point. So the fact that it comes back down is understood as natural. Okay. We can do alternative cuts through our parameter space. So I showed what if we fix the reduced Rayleigh number, meaning the kind of thermal forcing relative to the rotation rate, and then vary the Ekman number. Here we can fix the true Rayleigh number, so just the thermal forcing, and then vary the Ekman number. And that's a slightly different cut through this parameter space. What I'm showing is, again, the Nusselt number as a function of the reduced Rayleigh number. So I vary the Ekman number at fixed Rayleigh number. This changes the reduced Rayleigh number. The black symbols indicate the data from the reduced equations. The colored symbols indicate the full equations at different finite Rayleigh numbers. And it's important, or it's interesting to notice that the black line, first of all, is in rather good agreement with this dashed line here, which is the diffusivity-free scaling. But at finite Rayleigh numbers, that is only true at most over some range. And then the curves flatten out at higher reduced Rayleigh numbers, intersecting the reduced model curve at a certain value that's indicated by these vertical dashed lines. And when we look at where these vertical dashed lines are located in the reduced Rayleigh number, that corresponds to a transitional Ekman number of some sort, where we intersect with the reduced dynamics, and we kind of the Nusselt number starts leveling off. And if we just plot those these transitional Ekman numbers as a function of the Rayleigh number, which is the different sets of simulations shown here, then a power law is quite clearly visible. And that power law is, again, in agreement with the theoretical predictions from the boundary layer theory. So this is another data point that confirms that things are hanging together. OK. How much more time do I have? It's basically out of time, is that right? Or? No, 5 minutes, right? Yeah, 5 minutes. OK. We started a little late. Another way to so here we looked at heat transport, and another important feature of the flow is the thermal boundary layer. Here there are no Ekman boundary layers because we don't have no-slip boundaries, but nonetheless, because of the thermal boundary conditions penetrating for some depth into the domain, there is a thermal boundary layer, and we can quantify that in terms of the RMS of the temperature fluctuation, which is plotted here versus the coordinate z in a logarithmic scale, and it's normalized so that the maximum of this profile is always 1. And based on the location of the maximum, we can identify the top of the boundary layer. That's one of the established ways that people measure the depth of the thermal boundary layer. So we can first of all, look at this figure, where as the Ekman number is reduced at fixed reduced Rayleigh number, the boundary layer becomes thinner and thinner to the gray line, and then actually it thickens again. So the yellow line is slightly thicker than the gray line. So this indicates some kind of undershoot. As we just go decreasing Ekman number, it's not a monotonic dependence, and that's borne out if we repeat the experiment with more data points. At fixed reduced Rayleigh number, varying the Ekman number, there's an undershoot in the boundary layer depth. So as the heat transport overshoots, the boundary layer depth actually undershoots. And then there's a scaling law here that's slightly steeper than Ekman to the 1/3, and it's not quite clear where that comes from. The boundary layer depth converges at a constant at low Ekman numbers, and this constant is again in agreement with the non-hydrostatic QG equation. So one more angle in which there's agreement between the two. This being the small scale structure of the solution. There were a lot of questions about the RMS Rossby number. I don't think I have enough time to talk about that, or we can talk about that afterwards. Okay, okay. I don't want to offend anyone in the audience, so I guess I have to talk about it then. We measure the Rossby number based on. So this is locally defined. So this overbar should not be there. Locally defined in terms of comparing the advection term to the Coriolis force, and we can average this in a horizontal slice. So to do the RMS in the horizontal slice at each height. So we can define a local Rossby number at different depths in the domain. And that gives these curves shown here at the bottom. So it's as a profile, as a function of z, at different Ekman numbers, showing the Rossby RMS. And so in the bulk, it's pretty constant. So there's a certain value in the bulk, and then it's changing close to the boundary. If we zoom in by plotting it on a logarithmic scale in the boundary layer, we see that, in fact, there's a different value that's attained in the boundary layer. And here, there's a slightly more complicated structure, but close enough to the boundary, it also converges to a well-defined value in the boundary layer. So we can plot those Rossby numbers, a posteriori Rossby numbers, as a function of this combination of the Ekman number and the reduced Rayleigh number that's informed by the boundary layer theory that so accurately predicted where we depart from the reduced equations. And this is the Rossby number for two different values for each value of the reduced Rayleigh number. On top here, we have the value in the boundary layer, and on the bottom, we have the value in the bulk. And it's interesting that only under this rescaling do these curves collapse. If you do not take into account this rescaling based on the boundary layer theory, these curves are all over the place. But they collapse nicely. And one thing that we can infer is that if this dashed line is the predicted loss of rotational support in the boundary layer, then there's a well-defined true Rossby number on the order of 0.2 or so, where the flow loses rotational constraint in the boundary layer. Okay, so there's a self-similar scaling when plotting things according to the boundary layer theory. And we can summarize, or I'd like to summarize, everything I've shown you, in a sense, in this parameter space. So we've seen in the beginning the Ekman number and the Reynolds number spanning this very hard-to-access parameter space with these shaded areas indicating the state of the art. These symbols indicate where we want to be, and the blue symbols now are added on top of this, and that's the numerical simulations we performed. I should stress that this Rayleigh number here, based on the height of the layer, is really maybe not the ideal thing to look at, because advection is horizontally dominated. And so there's a big difference between whether I choose the horizontal or vertical scale here. So if you look at the value of the Reynolds number, it's important to keep in mind that this is based on the height of a very tall column, but advection is actually horizontally dominated. Okay, so we go 6 orders of magnitude beyond the state of the previous state of the art by adopting a very sort of slender domain and rescaling things accordingly. So in a sense, this is not a silver bullet. We've done everything we needed to do to get the adequate numerical scheme for this regime. And you see that going to higher Reynolds numbers is still extremely challenging, because higher resolution is needed for more turbulent flows. But I'll summarize by saying that I've described the non-hydrostatic QG equations, which arise from an asymptotic expansion. I introduced the rescaled formulation based on the scaling laws informed by the asymptotics. And this allowed us to do DNS at unprecedented Ekman numbers down to 10 to the minus 15, where the numerical evidence clearly points to a convergence between the Rins equations and the full equations, based on various aspects that I've described, including the global statistics and the symmetry of the flow, as well as the small-scale boundary layer structure. And the threshold where we depart from this reduced regime is quite accurately predicted by established boundary layer theory. So I'd invite you to look at these preprints if you're interested in seeing more. And future directions are manifold, but they include going to non-unity Prandtl numbers, alternative boundary conditions, internal heating, latitudinal variations, magnetic fields, and many more. So I think this is really kind of first step. Yeah. Thank you very much.